So now let's consider two random variables. Because in econometrics we study particularly the relationship between different random variables. Right? So it's very necessary knowledge here. So the first concept is the joint distribution. Okay? Suppose we have two random variables. How can we can describe their probability distribution together? Okay, basically we use joint distribution. Okay, it is the probability of two random variables or more random variables. Okay, simultaneously take certain values, say x and y. So for continuous random variables, we use cumulative distribution function, just like univariate random variable. Okay, so it's this capital F of x and y equal to the probability of this random variable x is less than or equal to this little x, and the y, capital Y, the random variable y, less than or equal to this little y. Okay, so this is the cumulative distribution function of x and y, the joint distribution of x and y. Okay, and again, you can obtain the density function by take derivatives with respect to x and y, okay, to get the density function. Again, if you have the density function, you want the cumulative distribution function CDF, you simply do the integral. Okay, and the marginal distribution, okay, is basically if I give you a joint distribution, but I don't want to know any information about y. I just want to know the distribution of x. Okay? But I give you the joint distribution. How can I recover the distribution of x? Okay? So what we do is basically integral y with respect to y. Okay? So we get the marginal distribution or marginal density. If suppose I give you a joint density of the joint distribution between x and y, you integral y, you get the joint density of x. Okay? So I will skip the concept of conditional distributions by far. I would like to talk about the concept of independence. Okay, suppose two random variables x and y. Okay, so they have a joint distribution, but we call them independently distributed, or they are independent if. So the intuition is that if we know one if we know the value of one of the variables provides no information about the other, right? So basically, the variability of x has no predictive power on y. That's the meaning, the intuitive statement of independence. Okay? But how can we formally represent it? So typically, if the definition is simply if the joint distribution can be decomposed to the product of the marginal distribution of x and y. Okay? If the joint distribution of x, y equal to the product of the marginal distribution of x and the marginal distribution of y, then we say that x and y are independent. So this also brings out two very important concepts, which is the covariance and correlation. Okay? Covariance measures the extent to which two random variables move together. Okay? How two random variables change together, okay, in the same direction or in the opposite direction. Okay? So how can we compute the covariance? Suppose give you two random variable x and y. So it's basically equal to the covariance of x and y. Sometimes we use the sigma xy. Okay, it equals the expectation of x minus the expectation of x, the mean of x times y minus the mean of y. Okay, and it equal to the expectation of x and y. Okay, the product of x y minus the product of expectation of x and the expectation of y. So if the covariance is greater than 0, then on average, when x is above its mean, y is also above its mean. Right? Basically, which intuitively, if x is larger, then y is larger. Okay, so that's the meaning of. So basically, it means that x and y change in the same direction. But if the correlation is negative, it means that x and y change in the opposite directions. Right? So if x is larger and the covariance is less than 0, y will be smaller. Okay? So this is related to the concept of independent. Suppose x and y are independent, it basically means that there's no covariance between x and y. Right? Change of x has no effect on the change of y. So the covariance between x and y equal to 0. And the covariance between x and x itself equal to the variance of x. Just replace this y to be x, you get the formula of variance of x, right? And another very useful formula is this. Okay, if you have this a1x plus b1 and a2 times y plus b2, okay? If you want to know the covariance between these two random variables, it is equal to a1 times a2 times covariance between x and y. Okay, so the constant has no effect on the covariance. Okay, but for this a1 and a2, we can sort of factoring them out, right? Sort of. And there's a very important inequality, that is the covariance between x and y, the absolute value of covariance between x and y is smaller than the product of sigma x times sigma y, the standard deviation of x and the standard deviation of y. Okay. So because of this, we have another kind of measurement-free the covariance, but another measurement of covariance, but it is measurement-free. Okay, this is the correlation coefficient. It equals to the covariance between x and y divided by the standard deviation, the product of standard deviation of x and the standard deviation of y. And because of this inequality, we will have that the correlation is between -1 and 1. Okay. Again, if two random variables are uncorrelated or are independent, then the correlation equal to 0. Right? So as an exercise, maybe you can try to do this one. Okay. So suppose we have this constant. It looks like similar, right? So for this one, uh, we will have the correlation of a1x plus b1 and a2x plus b2 equal to the covariance of a1x plus b1 a2 sorry y plus b2, okay, divided by the square root of variance of a1x plus b1 times the square root of variance of a2y plus b2, right? Okay, so you can use what we have learned before to get this. So this in the denominator, okay, this equal to, as we have learned, equal to a1, a2 times the covariance between x and the y. And this equal to the square root of a1 square of a sigma of x square, right? So it equals to the absolute value of a1 times x sigma x, and this similar equal to the absolute value of a2 sorry sigma y, right? So this equal to a1 a2 times the covariance between x and the y divided by the absolute value of a1 times the absolute value of a2 divided by the sigma x and sigma y. Okay, if a1 and a2 are positive, this is also equal to a1 and a2. Okay, so this equal to a1 and a2, and we get this cancel out. Right? We get the correlation. Then we get the correlation between x and y, which has the covariance between x and y divided by the sigma x times sigma y. But if a1, a2, a1, a2, the product between, of a1 and a2 is negative, okay, then we get this to be a negative number, and this is a positive number. Okay, so okay, so you cancel them out, but you have a negative sign here. Okay, so this is the covariance. There are a little bit more probability properties of variance and covariance. Okay, you can read it by yourself. Um, so the last thing that is very important for the probability theory is that I will again to study more about the normal distributions and introduce some related distributions. Okay, so we have seen that the normal distributions of this form. Okay, there are two parameters that characterize a normal distribution. That is, one is the mean, okay, mu, and the variance sigma squared. Okay? If you have these two parameters, you can specify normal distribution. Okay? For a special case, if mu equal to 0 and sigma squared equal to 1 or sigma equal to 1, then we will have a so-called standard normal distribution. Okay? And it is of this form. It's basically this one, but we replace sigma squared equal to 1, right? And replace mu equal to 0. Okay, it's the same. And for multivariate normal distribution, let me just skip it because it involve a little bit more notations from linear algebra. So I don't want this level of complication in our class. Um, so here there are some important properties of a normal distribution. Okay? You can read it by yourself. Okay, uh, it's um, it's important, but not very important, relevant to our class. But it's good if you know all of them. Okay? Um, and there are three very important distributions that I want to cover. At least you have some basic knowledge about this. Okay, so suppose you have n standard normal random variables. So this z1 from this z1 to zn, they are normally distributed, and all of them follows a standard normal distribution. Okay. Moreover, they are independent. Okay, so we use IID to denote uh, independent and identically distributed. Okay, IID. But in the MOOC that I require to watch, okay, they use another different notation, which is NID, right? Whatever. Okay, NID. So suppose the random variables are standard normal and independent, then this variable, which equal to the sum of zi squared, follows the so-called chi-square distribution with n degrees of freedom. Okay, this n is the kind of parameter for this distribution. This n is the number of z's. Okay, this is the chi-square distribution. It will be useful in in econometrics. Okay, very useful. And t distribution. Okay, suppose it's a little bit complicated, but not so much. Okay, uh, z, okay, is the standard normal distribution. Have a have sorry has the standard normal distribution. Okay, and x has a chi-square distribution with n degree of freedom. Okay, then we have this t random variable equals z divided by the square root of x divided by n. Okay, and this random variable t has a t distribution or student t distribution. Okay, again, the parameter is degree of freedom, which is this n. Okay? Finally, there's a so-called f distribution, and we have two. Now we have two chi-square distribution, chi-square distributed random variable x and y. Okay, x has a chi-square distribution with n degrees of freedom. Okay? Y has a chi-square distribution with m degrees of freedom. Then the random variable f, which equal to x divided by n divided by y divided by m. Okay, so this f is a random variable. Okay, it has a so-called f distribution with m degrees of freedom. So by far, I just want to you have an impression of this this distributions. Okay, it will be useful later. Okay, I will talk about more maybe. Okay, but not too much. Okay, just you have this concept of T and F distribution. Okay, know basically where it comes from. Okay. And this theorem I will leave it for the future. Okay, so this finishes our it's a very brief review on probability theory. Okay. Just go through some basic concepts, and by far maybe you are not aware of the usefulness in their usefulness in econometrics, but they turns out to be very useful. Okay, but especially for your understanding the theories, but in kind of in practice, maybe you just follow the procedures. It's not so relevant anyway. But I think it's very important for you to know not only the procedures to do econometrics, okay, but also why you are doing this. Okay, the fundamental rationale of the econometric analysis.